I will move to the next speaker. Next speaker is Dr. Miles from United States. He will talk about his calorimetric studies of palladium alloy cathode. Please.
What I'm going to talk, is this on? My talk today is on work I did in Japan. I work for the Navy, but since 1995 the Navy has not funded this area, so this is the only work I've done on cold fusion in the past 5 years. Was 5 months in Japan working at the New Hydrogen Energy Laboratory. I tried to collect as much data as I could in those 5 months. I knew I'd have a lot of time when I got back maybe to analyze the data later, look at the data and analyze it. And I'm still in the process of analyzing all the data I collected from Japan, and Martin Fleischmann is helping with some of the analysis. He'll speak on tomorrow about some of the data. I took with me to Japan my China Lake type cells, where the heat is transferred by conduction. I'm not going to talk about that today except to just summarize it. The first 2 experiments were 2 rods I'd run in China Lake. This one had given excess heat before. It gave excess heat again in Japan. This one did not give excess heat in China Lake, and it did not give excess heat in Japan either. And then I tried platinum particles and palladium particles, excess heat with the palladium particles, but none with the platinum particles. And this was a continuation of the same experiment where I went to a different type of electrolysis instead of constant current pulse with Dr. Tripodi's help. And the excess heat got larger, as you see, and still no excess heat in the, for the platinum material. So this summarizes very briefly the China Lake calorimetry. At all times I had 5 calorimeters running, 2 of my own from China Lake and 3 of the Fleischmann-Pons type, and that will be the focus of my talk today, is the Fleischmann-Pons calorimetry. But before I go into that, the China Lake calorimetry has been published. This came out just recently in Journal of Electroanalytical Chemistry, the February 29th issue of this year, 2000. I have some reprints with me I can give people if you're interested. If I run out, give me your card and I will send you a copy of this in the February issue of Journal of Electroanalytical Chemistry. I was surprised by that paper because both referees agreed to publication. I did not have much trouble. That's unusual in this field.
Yeah, but it was analytical chemistry.
The Fleischmann-Pons calorimetry, I ran various experiments. Some rods I took with me. These 2 were made by NRL, palladium cerium boron. The second one is palladium boron. The third one is the palladium cerium given to me previously by Martin Fleischmann. And that will be what I'm talking about today, these top 3. I also ran co-deposition. That's the Stan-Spock method, where you deposit palladium out of solution at the same time it's loaded with deuterium. All 3 of those produce excess heat. A preliminary report of this is published in Fusion Technology, September 1999. But Stan Spock and I are still working on the exact analysis of this data and hope to have a more detailed publication later. And then I also worked with Paulo Tripodi on electromigration using Fleischmann-Pons cells, but we ran rather short of time details of that study. So anyway, my talk today is on the Fleischmann-Pons calorimetry. These were cells shipped to Japan, similar to what Martin Fleischmann and Stan Pons had used previously in France. The cathode is here, of course, the anode, and it had 2 thermistors, a long thermistor and a short thermistor, so 2 temperature readings. Data was taken every 300 seconds or 5 minutes and recorded by data acquisition in the computer. But that's a typical Fleischmann-Pons type cell arrangement. The three studies I will talk about today, the palladium cerium boron made by NRL. This is 4.4 by 20.05 millimeters area and volume shown there. The palladium boron, which had been very successful in China Lake in producing excess heat. I'd had 7 out of 8 produce excess heat prior to Japan. And this one also produced excess heat, as we'll see, in Japan as well. The palladium cerium was given to me by Martin Fleischmann a few years earlier and produced excess heat in Japan, excess heat in China Lake. And I took it to Japan and produced excess heat also there. This is an earlier study on palladium boron. This was done at China Lake. One interesting feature shown here is excess heat starts very early, almost right at the beginning of the experiment, almost the first or second day, excess heat starts to appear. We see this also in the results in Japan. Excess heat sets in very early in this palladium boron experiment. And throughout this time period, of course, there's considerable excess heat in the China Lake experiment, published in the China Lake publication as shown above. But it's important to note that the excess heat starts very early because we'll talk about that a little bit more later. The palladium cerium also produced excess heat in China Lake. This is from the Navy report in the 1994, 1995. Well, this is 1994 data shown here, but it showed considerable excess heat, the palladium cerium rod. I used exactly the same rod again in Japan and also got excess heat. The palladium boron was a different palladium boron rod that I used in Japan than what I showed previously, however. Now this is the mathematics, and I don't know how much time I should take on this, but this is the power of the calorimeter. The power that goes in is electrical power and any excess power, if it's present. The heater power, when the heater is applied. The power going out is the heat lost due to radiation. Most of the heat transfer in this calorimeter is by radiation, in contrast to China Lake, where the heat is lost by conduction, and the power carried away by the gas stream. So that is your equation, but the terms get rather complicated. That's the electrical power in, that's the thermal neutral potential, the Faraday efficiency, which is 1 in all cases that I've ever ran. The power out, since this radiative transfer is to T to the 4th, and the radiative heat transfer coefficient. The power of the gas stream is rather complicated, but it involves heat capacities of the various gas species, deuterium gas, oxygen gas, D2O vapor leaving the cell, as well as the largest term actually is the power loss by evaporation, D2O changing from liquid to gas. That turns out to be the largest term there. The power of the calorimetry is this term right here. But the point I want to make is to do calorimetry accurately with this system, you have to have accurate values for the the radiative heat transfer coefficient, and what is called the water equivalent of the cell, the mass times the heat capacity of the cell. And these are 2 areas where the Japan analysis by NHE fell short. They did not establish good values for these key parameters. You cannot have accurate calorimetry unless you have those 2 parameters determined accurately, the radiative heat transfer coefficient and the water equivalent of the cell. Those are basically your 2 unknowns. The rest of these things you can calculate or measure. The way I do the calculations is I calculate all these heat capacity values at the temperature measured for the cell, because they can be expressed. This is from the literature, how these values vary with temperature, the various heat capacities, the heat of vaporization, how it varies with temperature, the vapor pressure of D2O, how it varies with temperature, and Because it's a LiOD solution, I multiply by 0.98 there, and the thermal neutral potential, how it varies with temperature. So I actually calculate all these values at the temperature of the measurement of the cell. And this can be easily done through modern computers using Excel spreadsheets. These equations are rather complicated, but computers handle them fairly easily. Now, the time constant of the Fleischmann-Pons calorimetry is about 90 minutes. Therefore, you need to average the data. I want to point out, just if you don't average the data and you take one data point, some error sources. The heat capacity of the water equivalent of the cell is 450 joules per degree. If you have an error in measurement from one point to another of only 1/100th of a degree, and multiply those two together, the data is taken every 300 seconds, you see an error of plus or minus 15 milliwatts. So that's purely because you're not averaging the data. This is all these errors are removed by averaging the data. The cell doesn't respond quickly to any change. It responds over a very long time period because it takes 90 minutes just to reach the time constant. And it takes several hours to reach a new equilibrium after you change a parameter like the cell current or add D2O. It takes several hours to come back to a near equilibrium. Your cell voltage measures due to gas bubbles, and you may have between two measurements plus or minus 2/100ths of a volt. And if you're running at 500 milliamps, that's an error of plus or minus 10 milliwatts. But if you average data, these errors are not are removed because your cell is averaging all the time. It's averaging everything that's going into it over a long time period. So because the cell is averaging the effects on it, you should average measurements that you make, and perhaps also measure the temperature to 1,000th of a degree, for example. That would help also, which we did in the data we had in Japan. Now, the NHE method, in my opinion, was very poor, fell far short of being accurate because it did not determine this radiative heat transfer coefficient accurately or the water equivalent of the cell. In fact, they just assumed a value for the water equivalent of the cell, to the best of my knowledge. They determined the heat transfer coefficient by the first application of the heater pulse. First time the heater was turned on, they calibrated for the entire experiment based on that first and only heating a cycle. And that's basing your whole experiment on one calibration, which is very incorrect in my opinion, because if anything is wrong with that one calibration, the whole experiment is off. And that's exactly what they did. They took the first cycle and used that to calibrate for the cell constant. You should do extensive work to determine what that cell constant is and make sure it's consistent throughout the experiment if you want accurate results. Even when they did apply the resistive heater, it was for too short a time period, only for 6 hours. For the time constant of these cells, you don't really quite get to equilibrium, so you don't get really a good measurement because the time period is too short. It should be applied more like 12 hours instead of 6 hours. They assumed a value of the water equivalent of the cell. I think it's actually 490 is what they assumed. And I don't know where they got that value, but they just used that in their computer calculations as the water equivalent of the cell, which is off. As far as I can tell, they did not average the data sufficiently. Martin Fleischmann, Stan Ponce had a handbook there that talks about averaging the data for 11 measurements or for over 55 minutes. You should use an average, either backward averaging or forward averaging, using 11 points, which would be over a 55-minute time span. But to my knowledge, NHE ignored that and used their own methods without this averaging taking place. I'm not aware of any blank experiments they ran to check that the calorimetry was performing properly based on the way they did their calculations. They should have ran blank cells using platinum cathodes with D2O, for example. And there was no measurement of atmospheric pressure at the laboratory. In the equation for the calorimetry, there is an expression that involves the vapor pressure of D2O and the atmospheric pressure. So you need to know what the atmospheric pressure is day by day to do these calculations, especially if you go to boil off. That's very important. This is data from Martin Fleischmann using my data I gave him from Japan on the palladium boron. This is a heating cycle that Japan based their calibration on. This is the cell temperature. It's gradually going down. You apply the heating cycle, the temperature goes up, but you see it doesn't really reach an equilibrium. The time period is too short. And furthermore, when you turn the heater off, it does not relax completely back to what the baseline should have been. If you put a straight edge here, maybe you can't see it from here, but it should come back to the same baseline, which would be about right here. The temperature does not come back to that baseline, showing there was positive feedback. And you had excess heat during that heating cycle, and that continued after you turned the heating cycle off. And that's also a reason why this didn't level out very good up here, because excess heat was being produced, and it was increasing as you were increasing the temperature. So they could not in any way get a good calibration based on that heating cycle. And that is the only heating cycle they used in the entire experiment to get the radiative heat transfer coefficient, which is completely wrong. They got a wrong constant and therefore wrong results. This is the cell voltage. Of course, when the temperature goes up, the cell voltage goes down, as you would expect. And then when the temperature starts to fall, the cell voltage goes up again. But you should look at heating cycles like this and look for evidence of positive feedback. And before you determine, you can use that for the calibration. This is data I plotted out of another heating cycle. We turn on the calibration heater comes on. Here it does level out better because there's no positive feedback, or very little in this case. And you see it relaxes back. I drew a straight line here, and it relaxes back to about the same baseline. So in this case, it looks like there was not a serious problem, perhaps, with positive feedback. Again, the cell voltage, when the temperature goes up, the cell voltage goes down. But it comes back to about the same basis. And you can see you need to average the cell voltage because of the fluctuations that go through. You have to use an average value for cell voltage. I plotted this out point by point on large chart paper. This is rather tedious. It takes maybe 2 hours to plot a data point like this, but it's a good exercise to test what's going on in your system. In the limited time I have in Japan, only 5 months, and running 5 different experiments, I did not have time to work out details of exact analysis. I knew that the way NHE was doing it was wrong, and I did not want to just let it go on what they were telling me. So I tried to find my own method, which is not as good as Fleischmann's, but I think it worked to some degree. I used exact calorimetric equations with no approximation starting out. I tried to use near steady-state conditions where the water equivalent errors would be minimized because the change of temperature is very, very small. So I used time periods where the cell had reached near equilibrium and the temperature was not changing rapidly. Therefore, errors due to the water equivalent term would not be too large. And then I used an estimated value for that, since I had no way of determining it exactly. Japan told me it was 490, but Martin later found out in his data found out it was 450. So 450 should have been the value instead of 490. I determined a pseudo-radiative heat transfer coefficient by assuming there's no excess heat. And then I found periods where these heat transfer coefficients, assuming no excess heat, are high. Those would be periods where the excess heat was either low, because excess heat will make your heat transfer coefficient go down if you assume there's no excess power. So I calculated the heat transfer coefficient and then used periods where it were high, where therefore the excess heat would be small or zero, and used that for my heat transfer coefficient as an approximation. And then I used this value going back into the equation to calculate what the excess power would be. So the first experiment I did this on was the palladium cerium boron alloy. This is my heat transfer coefficient that I came up with, and I used this value, which is too high. I found out later, but I used this value. But I used data where the temperature change was small, so this would not be a big error. And for the palladium cerium boron, there's not much excess power. So this showed that this method was working to approximate degree at least. There's no significant excess power. There are fluctuations, but no large excess power effects using the method I'd worked out while I was in Japan. Now, when I applied this same method to the palladium boron, I got a different result. There was excess power. There was even a small excess power even starting out early in the experiment, but there were two large bands of excess power, a large band through here, through this region, and then less excess power through a large time period, and then another band of excess power later in the experiment, using this value. Now, as Martin Fleischmann will mention tomorrow perhaps, this constant is too small. It should be around 8.5 instead of 8.1. And this value should be around 450. But I do have the data. If I use the Martin Fleischmann method, which is, in my opinion, much more exact, that he's worked out, his data analysis he's given me, maybe he'll mention this tomorrow as well, he uses a larger constant for the radiative heat transfer coefficient, and then a smaller value for the water equivalent of the cell. But he does get these two bands, a band here of excess power and another band over here. In fact, if you compare his results and my results, we don't have quite the same time scales or the same power scale. This is excess power here, this is time scales here. But you can see we both show a band here and we both show a band here. And in fact, quite a few of the points, if you line them up, like right through there, those points go up and down in fairly consistent manner in that period. Or since the time scales are different, I can shift this over. That earlier period, there's a large peak that goes up and comes down, and then there's a band right in here. So you can see that the two methods are giving pretty good agreement. The main difference is that the Fleischmann method, which I'm sure is more accurate, much more detailed in determining the heat transfer coefficient, shows higher excess power than what I reported. This is in excess enthalpy, but that would be equal to 0.347 watts right there. So you're in excess of 300 milliwatts, or 0.3 watts over in this region right here. But it's remarkable that two different methods, the one I worked out in Japan and what Martin Fleischmann did, we show exactly the same features. The basic features are both present. Now, if you look at what Japan reported, what their data shows, they come up with a much smaller radiative heat transfer coefficient because they use that first heating cycle where there is positive feedback, therefore large errors. Therefore, they came up with a much smaller constant, and they use a much larger value here. They do show some bands here, but look where they put 0. They put 0 right through here, so they say Fleischmann-Pons calorimetry is very inaccurate. You have large fluctuations. What they should say is there's excess heat fluctuations and their calibration is off. That would be more accurate. But they do show some of the same features, but they just have calibrated it incorrectly. So what, 5 minutes? Yeah. Right. Okay, I'll just try to hurry on through this. And this is the palladium cerium. It also shows excess power, reaching high as maybe 200 milliwatts through here. And again, the NHE method in Japan, they say there was no excess heat in this experiment. And in fact, the Japanese report, despite my writing this up and before I left Japan and showing these results to them, the Japanese report boils it down to one paragraph and says that I had no excess heat, which I don't understand. But I think there's always a problem when you try to transfer a calorimetry to another laboratory. If the other laboratory doesn't understand it, doesn't do it right, they're not going to get the correct results. So Fleischmann, when he tried to transfer his calorimetry to NHE in Japan, they changed things. They used their own method of data analysis. They got things incorrect, and they claimed there's no excess heat, and they reported there's errors in the calorimetry. I had the same problem when I tried to transfer China Lake calorimetry to NRL. Even though I tried to show them exactly what I was doing when I got back to Naval Research Laboratory, they wanted a larger cell so they could do loading studies, so they scaled it up. They added 4 extra lead wires. Even though we told them about data averaging, they did not average the cell voltage and temperature like they should have. And they had a very poor room where the temperature is out of control. And therefore, when they wrote their final report, they reported an error of plus or minus 200 milliwatts in their calorimetry. Well, mine only had an error of plus or minus 20 milliwatts. And for a year or two, I thought they were improving things. And towards the end of the program, I found they increased the error by a factor of 10. And since I've never seen anything larger than 500 milliwatts, they would not see anything either with that kind of error. So I had the similar experience trying to transfer calorimetry to a different laboratory. Summary, the Fleischmann-Pons calorimetry, you have to get an accurate determination of the radiative heat transfer coefficient and the water equivalent of the cell, or you should not even try to use it if you're not going to try very hard to get those things right. The alternative NHE method, which is published in the Monte Carlo meeting, is a complete failure. I would cross that article out if it were me, if you go back to that publication. The heat transfer coefficient is determined incorrectly, as well as the water equivalent of the cell. And therefore, the NHE method confuses excess power with the error of the Fleischmann-Pons calorimetry. In this study, palladium boron and palladium cerium showed significant excess power in the Fleischmann-Pons cell, even though the NHE report does not acknowledge that in Japan. And just a note, I hate being critical of Dr. Sami and people at NHE. They were very good friends, but scientifically they did things wrong. So I have no choice to take this stand. But I did very much enjoy working with the people in Japan while I was there. And just acknowledgement, NEDO, New Energy Development Organization, I'd like to express appreciation to them for this 5-month period I had in Japan. And the people I worked with at New Hydrogen Energy Laboratory, Dr. Sami and Sumi and Marie Hosado. And also I'd like to thank my wife who did a lot of help on her computer and typing to make all this possible. Okay, thank you.
Thank you very much. Now we have a time to discuss.
Just a simple question. How do you compare the data of palladium cerium and palladium boron? Which gives more excess power?
In this experiment, the palladium boron gave maybe 100 milliwatts more. The palladium cerium was about 200 milliwatts, and the palladium boron is maybe 350 to 400 milliwatts in this case.
What's the current you're using, and what was the temperature? You mentioned that.
The current, typically the current was between 400 to 600 milliamps. And what was the other question?
The temperature?
The temperature, typically 50 to 60, in the range of the 50s or 60s degrees Celsius, except we later drove this cell to boiling, and maybe Martin will talk about that tomorrow. The excess heat even got larger during the boil-off period.
Did you start by loading at low current, or did you go directly to the high current?
I started off by loading at 150 milliamps for 3 days.
But you don't show that?
No, I didn't show that here.
Okay.
Right. Well, it was a very early, the first heating cycle was at the low current, 150 milliamps, that Japan used for that calibration. So that calibration, that first calibration was low current, 150 milliamps. That's another possible problem. They calibrated at a much lower temperature than where we normally ran. They calibrated that first heating cycle where it was still low current and still doing loading, 150 milliamps. The still temperature is probably only about 30 degrees during that first calibration that they used.
Could you comment on Ed Storm's work yesterday with respect to using heating as a technique, using a heater as a technique for calibration as opposed to using the electrolytic power, which he had two curves in his yesterday. I'm a little curious about how you would judge Ed's result and comments and the whole process that you and Martin have used.
Martin, do you want to answer that?
I just want to say, I'll say something about that tomorrow, but Ed is wrong. If the cell is adequately stirred, then of course you can use the heater power. But you must apply the heater power while the cathode process is going on. You must have the same rate of stirring. Otherwise, of course, you might have any old thing.
I think I would agree. I've used both, actually. I've calibrated by increasing the current of the cell and use that as a calibration, and that seems to give a fairly good result. But I think the heating pulse is maybe more accurate in the end.
Can you say something about the relative accuracy of the calibration?
In my opinion, using this heater in the cell is more accurate, in my opinion, than just increasing the current and using that as a calibration. And for any of these, you have to assume that the excess heat is not changing. Either it's absent or is not changing, or else that's going to throw it off anyway.
Comment about that. Yeah, he's doing electrochemistry as well as heating. That's why it's correct.
Right.
Ed was doing separately.
Oh, okay. Okay. If you're not doing any electrochemistry, then the heater is probably not too accurate. And I've tried this at China Lake too. You have to devise some method for stirring. If you're just going to use a heater and no electrolysis, there's no gas bubbles to stir. So you have to devise something else to stir it. Otherwise, it'll be very inaccurate. Right.
No more? Well, has NHE ever responded to these criticisms?
This happened several months ago, and I was periodically corresponding to Dr. Sami and Mr. Matsui by email, and when this happened with Jed Rothwell and so on, I wrote a letter, a real nice letter to him, just explaining that I had to stick by what I thought was correct scientifically, but I told him I very much enjoyed working with him in Japan, and I've never heard from him since. So.
Okay, thank you very much again. So,
Here. Another bottle over there.
now we will.
Did you get some?
Oh, no, not yet.
You wanted some water, didn't you? Yeah. Here. You want water?
We will move to the next speaker. The next speaker is Professor Kim from Purdue University. He will talk about the ultra-low energy nuclear fusion for both nuclei confined in ion traps. Please.
This is the outline of my talk. What I'm going to tell you, is new since last conference, and completely different than existing theories, including mine. All of the mathematical details in all of the mathematical derivation is published, so I won't go into detail of the derivations of the theory. I will just outline how we do. The motivation of doing this so-called coherent quantum state nuclear fusion which is more or less aim of the preparator or other theorists in this room, came from work on Bose-Einstein condensation, which was a completely different subject. We developed a theoretical method to do that part, and then realized that we can apply this to coherent quantum state nuclear fusion. But before I get into that new approach, let me remind you what the problem is with the conventional theory. The several speakers has mentioned the gamma factor, and actually it's very simple derivation in undergraduate quantum mechanics book, and you get this factor here. But I like to remind you that this is not the fundamental derivation. It's the WKB approximation. I think one should really realize that this is not first principle derivations, which many of my colleagues in nuclear physics forget. What we like to look at is essentially those three reactions. I'll discuss these two reactions, and then finally this transition without no gamma rays. Now, if you take gamma factor, you get this kind of number. Look at this number. I don't think this makes a physical sense. Even with the electron scattering, it's extremely small. And of course, Kasagi is claiming you have to put electron screening energy of this order to explain its data. And the original Fleischmann-Pons, if you extract from their data, is 10 to the minus 20, and Steve Jones' claim will correspond to about 10 or 12 order of magnitude lower. So this is a benchmark figure we'll work with. Now, in terms of rate, again, you can have a benchmark work. Notice this number I'm going to use later on. Fleischmann-Pons is about this rate per deuterium, and Steve Jones will be at this point. And it's nowhere near this number. Okay, now that is sort of background. Does the gamma factor derivation can we improve that? And we did look at from a quantum mechanical point of view, and derived a formula based upon quantum scattering theory, which I regard to be more rigorous. And in fact, one can use optical theorem, which is very rigorous result, to turn around and get new formula. And when we did that, we came up with modification of a gamma factor. And instead of ordinary form we had before, this is extra factor you obtain by doing quantum scattering calculation using optical theorem. So there are large uncertainty in gamma factor. Now, I won't go into more than that because I like to dwell on different theory. And this was originally last conference. We speculated that possibly Bose-Einstein condensation mechanism might help us to explain many of the data. But we realized that we are just borrowing Bose-Einstein condensation for the atoms, which is neutral bosons, while the deuteriums or charged particles. So the same formulation should not be applicable. So we had to reformulate the theory to come up with this question. Now, what we are trying to do is trying to solve this many-body Schrödinger equation. It's easy to write and very rigorous, but in order to get the solution, it's not that easy. So, but before I do that, try to discuss approximate solution. Let me retest this same many-body Schrödinger equation in terms of creation annihilation operator. And the reason I like to mention this is that Dirac, in 1933 quantum mechanics book, in one of the chapters, made this statement that for large n bosons, this commutator, instead of this Kronecker delta, can be set to 0 because operator, expectation value of operator are so large. And physical consequence of that, he states that is interacting bosons behave like independent particle, although there is an interaction between them, that interaction becomes sort of background potential. So the interaction between pairs are washed out. Now that is very interesting, important conjecture. No one has proven it, but we'll see our results are consistent with his conjecture. Now, conventional Bose-Einstein condensation is mostly used this so-called Ginzburg-Gross-Pitevsky equation, and this is a nonlinear Schrödinger equation you derive. But in order to derive this, your interaction has to be contact interaction, not repulsive Coulomb type. So now I'm going to describe how we solve this problem. We invented this method of so-called equivalent linear two-body method for charged boson. And what it is that you're trying to obtain your many-body wave function, but that's very difficult exactly. So what we do is we'll approximate this with some sort of trial wave function in which those three parameters are like a x, y, z coordinate. So instead of 3 times n degree of freedom goes to 3 degree of freedom, which we can solve. And by putting this in variational principle, one can generate an equation which is two-body equation. And that we know how to solve. We have tested this with a number of different exactly known solutions, like a one-dimensional case, and found that this method is very accurate for very large n. And later you see we are talking about million particles in a trap. So this may be a reasonable approximation. So to do the charged particle many-body problem, we start with this many-body Hamiltonian. And notice that I am including Coulomb interaction from the beginning. That is, all the pairwise Coulomb interaction is explicitly included. They are in harmonic oscillator confining potential and trying to get the exact solution of this Hamiltonian. And we use this ELTB method and then come up with this two-body equations. And everyone knows how to solve two-body Schrödinger equation. this is almost looking like a Schrödinger equation in this coordinate row, which is defined here. This looks like a centrifugal term, and very similar. And the potential, effective potential, becomes something like that. Now remember, this equation came out of the original Hamiltonian, which include all pairwise Coulomb interactions. Now we can solve this equation, and I won't go into the detail. For large n, we can get sometimes the exact solution, but I'll skip that part of derivation because most of you may not be interested in the mathematics of it. But let me see, once we solve that equation, we have a wave function, eigenvalue, and eigenfunctions, and that function is many-body wave function. Now, in order to calculate the nuclear fusion process, one has to have transition operator, which is a nuclear potential. That is, initial many-body state will, two pair in a many-body state will interact through the nuclear interaction. And then make a transition to final state. So now we have to introduce short-range nuclear interaction operator to really calculate transition probabilities. And we go back to our optical theorem formulation, in which we show that scattering amplitude can be related to a cross-section in this way, and so that whatever form of the short-range nuclear interaction you assume, one can make a connection to real nuclear scattering parameters. And we can relate our interaction or coupling strength with the known experimental number. This is the S factor you extract from the low energy data. Remember, this S factor is nearly constant, whereas the gamma factor is the one which changes so much. So the whatever potential you assume, this is called the Fermi potential, essentially contact interaction, delta function interaction. But whatever interaction you assume, you have to determine what is the coupling constant, appropriate coupling constant. And that's given by A, and A is related to known experimental number. So we can essentially use the experimental number to describe this transition operator. So that's taken care of. Fusion rate can be computed as a transition rate using a transition operator. Remember, this is a pairwise interaction, so I have to do all of the deuterium pair in the system. And if we use our solution, the wave functions, approximate wave function, then it becomes this form. And this can be computed using our solution. And let me now go into a single track deuteriums of both nuclei confined in a single track. That rate, after we do the calculation, becomes something like that. Now, omega squared, remember, is the harmonic oscillator parameter, but that can be related to size of harmonic oscillator. So we get the one prediction or formula which look like this. If you now, instead of parameter omega square, if you relate that to the average size of the oscillator, by using our ground state expectation value, we can calculate that. So this parameter is essentially translated into size of the confining potential. And if we put all that, we get that one. Now, remember, B is non-constant coming from nuclear interaction. Omega is the one we cannot calculate. That is the probability of